Hey, Nate.
Yeah, Sam.
Do you ever wonder about all the data that's out there about you just kind of floating around in the universe?
Yeah, every time I open up a social media app, there's a targeted ad for something that I've searched for or talked about, and I'm sure there's just a ton of data about me out there.
I guess the thing that's always sort of given me some comfort is I assume that there's just more data than anybody knows what to do with.
Right, but how do statisticians work with that data?
Right, and what is this thing called big data that we keep hearing about, and why is it getting bigger?
I don't know.
Hey,
I got a question about that. Welcome to another episode of Hey, I Got a Question About That.
I'm Sam.
I'm Nate, and this is a podcast and video series where we talk about all the research going on here at the Penn State Eberly College of Science.
Today on the pod, we're joined by Francesca. She is the Huck Chair for Statistics in the Life Sciences in the college.
Yep.
And Francesca develops methods for the analysis of big, complex data.
Yeah, it's a great podcast we have here, so let's check it out.
We are joined here in the studio today by Francesca Chiaramonte. She is the Huck Chair for Statistics in the Life Sciences at Penn State. Thanks for joining us, Francesca.
You're most welcome. Happy to be here.
And we're going to talk about big data and kind of what makes it big. So maybe you can start there and tell us, how does data get big?
All right. So actually, data gets big in at least a couple of different ways. And one way to think about this, just to visualize it, imagine a spreadsheet. Okay, it's got rows and columns. Think of the rows as the units, the people, the mice, the experiments on which certain things are measured, and the columns as the things that get measured. Okay, so in the last 20 or 30 years, there have been two main trends. And perhaps historically, the first is the one that has brought the number of columns to increase, okay, in a very, very dramatic way. Perhaps a bit shifted in time with respect to this. There have been also things that have started making the number of rows, the number of units, increase dramatically. So let's start with the columns, and the columns would be the number of things that get measured on each of the units that are observed. One classical example of how this, which in statistical jargon is called P, the number of features measured, has increased over time, has to do with the so-called omics, right? When I first arrived at Penn State in the late 90s, it was the period when microarrays got created first. And this essentially shifted the paradigm from a situation in which you could measure one or a few genes and their behavior in any given sample to a situation in which you could measure the behavior of thousands of genes at once. Over time, this got perfected with different types of technologies, okay? Often we talk about high throughput technologies. And these, again, are things that essentially allow you to take a unit and snapshot it in a way that concerns thousands or tens of thousands or perhaps even millions of ways.
So when you say omics, you're talking about things like genomics or proteomics.
Exactly.
And that's just sort of this idea that we study the massive amounts of information in these particular fields, kind of?
Yes. And
looking at the whole
the example about the genes, perhaps you could say, goes under the label of transcriptomics. Okay? You are trying to assess how much genes are transcribed, are used in a particular sample. That could be, a sample from the liver of a human, for instance, or, again, of a mouse, just to make it simple. So the number of columns of this spreadsheet is growing and growing and growing over time. Why would that matter from the point of view of analyzing the data? So traditionally, statistics copes with situations in which you have a phenomenon that is characterized in a certain dimension, and then you get to replicate observations of it, the units in this case, okay, many, many times over. A lot of statistical theory, all we know about the way statistical procedures perform to tease certain signals out, has to do with the fact that the number of replicate observations that you can have on this phenomenon grows it's large relative to the dimension in which the phenomenon lives, and in principle can be brought to infinity. Okay?
And so the kind of concept of dimension in statistics has always been something that I've had a little bit of trouble wrapping my head around. Can you explain that a little more?
In the type of things that I have in mind right now, it's actually rather simple.
Okay.
Okay? You have a person, and you're measuring 10 things on this person. That makes a vector of dimension 10. Or you're measuring 100 things on this person. The dimension of the vector becomes 100. You're measuring 1,000,000 things on this person. The dimension of the vector becomes 1,000,000. So for each row, you're going to have 1,000,000 numbers, okay, for 1,000,000 columns.
Right. So for things like microarrays, you might have 1,000,000 different little gene mutations or something that you're measuring
So
per
these
individual.
In the case of microarrays, actually you have one number for each gene.
Okay.
So that can be 6,000, it can be 20,000, in this type of order of magnitude. But you're right, and I'm glad you brought it up. There's another type of dimensionally very large type of data that has to do with variance in the genome.
Okay.
The simplest type being the SNPs, the changes at individual positions in the genome. What makes that one very interesting is that it moves the ball another little bit. Okay, if you're using a microarray to measure gene expression in samples from the human body, you have a certain number in the order of 20,000. Okay, these are the genes, and you could kind of take that to be fixed. If you're measuring mutations, variants in the genome of a person with next generation sequencing techniques, the number of mutations you find altogether increases with the number of people you look at. So P, the number of columns in our spreadsheet, is not just very large. It is actually such that if I'm trying to increase N, the number of rows, P moves with it. Okay?
Yeah.
All right. This actually, it's yet more interesting from a statistical point of view because, again, the idea was, okay, I've got something characterized in P dimension. P can be very large, but at least theoretically, I can look at it more and more and more and more and more and more and more until I looked at it a lot and I know what's there. If when I look more, the thing grows, the paradigm shifts completely. And in fact, statisticians have had to develop a new way of doing what we call asymptotics, in which we prove the properties and the good behavior of certain statistical procedures, even allowing this fact that as you look more, the thing gets bigger, as long as it doesn't grow too fast.
Right.
Okay? So you can see here how this whole new world of fast increasing P has changed statistics in a profound way.
And so as part of that, there's an issue, right? If the dimensionality, the number of things that you're measuring is bigger than your sample size.
Absolutely. And I was going to get there because that's an issue, actually, even if P doesn't run off with N. If P, the number of columns, is larger than N, the number of statistical units, or you can think of it as the amount of replication that you have about this phenomenon, a lot of standard statistics doesn't work as well. This actually is a very interesting boundary where you can really see how statistics has shaped, the domain science. And conversely, the questions in the domain science have forced statistics to develop into whole new areas. So how you do statistics when P is larger than N is something that statisticians have been hard at work on for the last 20 plus years. It's become literally a whole branch of statistics because the procedures that work well when you have abundant replications don't necessarily work well. They're not stable. They're not reliable, okay, when you don't. So statisticians have had to come up with new ways of doing things that would ensure a certain amount of stability, to say the least, as well as ways, which is kind of the crux here, to take a very big problem and make it smaller.
Right.
Okay? So if you have a problem with P in the tens of thousands, hundreds of thousands, possibly the millions, one approach to it is to say, okay, I'm going to try and see if I can bring this number down a lot prior to doing other things on the data. And so there is a whole field of statistics that has to do with reducing the size of the P size
Right.
of the problem. And this can be done either throwing some of the measurements away, essentially deciding that they're not relevant to the type of signals that you want to characterize, or with combining some of these P measurements into summary measurements, okay? They can be linear combinations of the original measurements, just to say one simple thing, or more complicated sort of combined
Sure. So
variables.
say if two of those measurements were sort of always correlated, you could treat them as one. Or
That is one principle by which you can reduce. Another one is whether they matter for your purposes. Let's say that you are facing a prediction problem in which you're trying to predict a certain outcome, a certain response. Then some features may not matter for that purpose, okay? Whether or not they're highly correlated with some other of the features that you have at your disposal. Of course, one of the things that most typically happens when you increase P is that as you throw things in the pot, more and more things tend to be correlated with each other.
Sure.
And this causes a whole other class of issues. But anyway, the statistics of taking a big problem and trying to make it smaller has been very, very important in the last 20 years or so, in various facets. Selecting features, feature selection, feature screens, as well as combining features. Sometimes this goes under the name of dimension reduction, but there are many, many variants, and then it gets technical. But the general idea is to try and take one of these problems that has become oddly non-square or non-rectangular in a
Sure.
vertical way. It's run amok horizontally and try to make it back into a problem that can be handled more reliably.
So how does, in terms of personalized medicine, how does P getting bigger affect that or play into that?
So let's go back a few years, if you will. One way of thinking of precision medicine is that you get to measure a very, very large set of features on a person, and this can go from their omics, the fact that they may have some specific variants that make them more or less responsive to certain intervention, to their other omics characteristics that they could have. One very popular example right now is the composition of their microbiomes. Okay, so you can measure these type of things. You can measure a lot of clinical variables in them. You can sometimes also measure variables that have to do with the environment in which they live. The latest frontier, if you want, is that you can have them wear devices that produce an enormous amount of data. You can have medical imaging on them. This produces an enormous quantity of information that could be used to tailor, okay, our understanding of what may be wrong with this person and the interventions that we may want to put in place. However, in order for this very large amount of numbers to tell us something useful about what should be done or should not be done to this person or with this person, we need to have trained the models, the prediction machineries that allow us to put these numbers in and get some meaningful answers out. To train this machinery, we need to have had lots and lots and lots of instances, okay, of how all these things turn into an outcome, okay? And the larger is the set of things, okay, that would be P, the more delicate it becomes to properly train these machineries that are going to produce a prediction. Now, as long as producing many instances of this, many people, okay, for which we know all these things in entry and possibly some medical outcomes in output, okay, as long as taking all these things in entry on units for which we also know some medical outputs or other phenotypes of theirs that are relevant, is quite expensive, you will always have a problem with making n large enough to properly fill the P. Okay? So it is also true that making n larger is a recent trend. Okay? In many of these studies, you try and make n as large as possible.
So to deal with this ever-growing number of things we can measure on people, then the answer is to measure more people, right? But
in a way,
but,
yes.
But is that the other way data gets big?
Exactly. And in fact, sometimes you measure more and more people even without P getting very big, okay? And, this may fit the bill a bit better with respect to what people think when you say big data. They think Facebook, okay? Or they think electronic medical records. So in electronic medical records, there are indeed a lot of things, okay, measured. Or, the online platforms, social media is a way you can create data where you have millions of units. And you may decide to measure a few things or a lot of things, but sort of this first order wow thing is the number of units. Okay, and these are just some examples. You can think of others. Remote sensing. Okay, things that we can do with satellites and other sensing devices right now. So in general, due to technologies that are kind of different from the ones that I was calling high throughput before, we've gone through a couple of decades in which our ability to grab individuals, units, and measure things on them has increased and increased and increased. And of course, this goes together with the possibility of actually storing, handling, and chewing on this data. Okay, so there is a computational ability issue also that is behind this trend. So when n gets very big, you may think, okay, that's great. What's wrong with that, right? You're getting more and more and more information, whether you're trying to study some kind of social phenomenon that you can grab information about through Facebook or maybe Google searches, which are in many ways considered more informative than what you grab from social media, because they're supposed to give you a better picture of what people think and feel and want to ask. So be that, okay, or be that a biomedical type of investigation in which you're trying to see how people, to measure a few things on an extremely large number of people. Or be that the ability to measure certain variables on many locations, many times over, increasing spatial and temporal resolution in the observation of certain phenomenon. You end up with this massive amount of units. And the problem there may become that even if you're trying to do something very, very simple, involving a few variables and a relatively easy statistical calculation, this is just so massive that you can run into trouble. Just feeding the whole thing in can be problematic. And in fact, sometimes you cannot even feed the whole thing in because different millions of people on which you're measuring something are actually stored on different physical locations, and it's not even possible to put all the data in the same place to then run a calculation. Sometimes you need these calculations run literally in real time, right? I was about to say because you have to send the right app, but the right ad, but
absolutely.
That's so. Even when n gets very big, and you may think that from the point of view of a statistician, this is great, right? You get more and more and more replication on this phenomenon that you're trying to understand. That actually poses issues too, and so also there, statisticians have been working to try and develop approaches to this, where you can essentially split the data, either by subsampling them or by partitioning them, in ways that allow you to, I'll be very rough here, but perform calculations locally on the periphery and then put them together in a meaningful way. So this too elicits a whole front of methodological research. But there was another thing that I wanted to say on this, which is that besides the issue of running computations properly and quickly on an enormous amount of data that may be, non-mergeable, maybe and you may also need to do this really quickly because you need answers in real time. In addition to all of this, with the big data in the sense of lots of units, there is another issue that I consider very important, and it's an issue of the biases that you drag in.
Sure.
Okay? So when you make a sample of 500 mice, okay, to measure their transcriptome, you usually think about how you select these mice. Okay? There are some randomizations, there are some guarantees that these units are not carrying specific biases. You have some control on how you do this.
Sure.
And this is the case also in some more survey type studies, right? In which you form a sample of individuals and you try and make sure by stratifying it or controlling certain elements of how you put the data together that the data does not carry blatant biases of some kind. Okay? There are ways statisticians do this. If you get into all the Google searches, okay, there's no way of doing this properly. If you know enough about the units that are searching, you can ex post kind of stratify certain things. People do this, put Google searches on a side for a second, with medical records. You have lots of medical records, and you can try and tailor a pseudo sample. Okay, if you know enough about the people, you can say, okay, I want to take this many people at random that fit these characteristics and make sure that I'm not skewing myself towards one specific type or another specific type in a way that is damaging to the type of study that I want to make, the type of answers that I need to get out of the study. But so big data is what it is. Okay, you produce it dragging a net, is that the expression?
Yeah.
And it can have all sorts of biases in it.
Can I try to see if I can
Go.
put this into an example that maybe I can wrap my head around? But so when you increase that number of units, the number of people that you're measuring.
Yeah.
So if there's some substructure within that sample, so say you're studying something that has multiple causes and you have a group of those people that have one cause and a group that has the other cause.
Or there may be people that are a lot more likely to be looked at because they're,
Okay.
they are under 35 and this is Twitter.
But
I don't know.
Yeah. So if you're looking at all those people at the same time, some of that could get kind of muddled in the statistics.
So I guess what I was trying to say is that getting overly excited about the fact of having enormous N's,
Yeah.
okay, is wrong, because you may have an enormous N, but not necessarily one that allows you to look at a phenomenon, okay, in an unbiased fashion.
Right.
Okay, you can have lots of information, but information that carries certain biases, and this kind of goes to a philosophical point, at least in my mind. Statistics historically is the science of accounting for and controlling error. Okay? You measure things with some uncertainty. There are sources of stochasticity that come in, and statistical procedures serve to control for these, account for these in a way that allows you to extract the signals. But errors are kind of thought of as benevolent or relatively benevolent. Okay? It's error. It's not bias. It's not.
So if you have
Of
random.
course, yeah. This I'm being overly simplistic here. In lots of
Sure.
data that were collected also before big data, there are known biases that can come in because of how the data is collected. But then you have ways of thinking about them and pre-processing the data or manipulate the data or modify your procedures to control. But in essence, it's about error and biases that you can rationalize and try to counteract for. With this super big data, error, as we are used to think of it, kind of burns away, because if you can shoot millions of observations to something, everything is significant. But famous adage, poop in, poop out. Okay, if what you're looking at contains very serious biases, your conclusions may be completely misleading. And turning statistics into a science of biases, of understanding biases and counteracting biases, changes its nature. Okay? I've been very philosophical here and very abstract. I can't give you concrete examples of how this needs to be done, but it's becoming a need if we want to make good use of these massive data that accumulates even just by attrition in our lives at this point. Okay? So there's no design behind how it is put together. We're going to have to be smart about the biases that come with it.
So I think you said something that I wanted to touch on.
Go.
It was a little point, but you said before big data. So what do you think has brought big data to the forefront now? Why is it so popular? Was it Facebook, or do we just have the technology now to be able to handle this data?
Because we have it. And in a sense, in some cases, we have it because of an effort. Okay? In some cases, we have it just because we have it. Because it's produced, again, almost by attrition, by the way we run our lives today. And you can see this as an enormous opportunity. It is. To do all sorts of science, okay? Social science, biomedical science, and lots of different things. But we should also be very wary of how we use them, besides the fact that we should also be wary about how we collect them by attrition and how we treat them, but that's a whole other...
Right.
But, the point is, I think, in many instances that we have it. Sometimes we also make a concerted effort to get it, and sometimes also a very expensive effort to get it, okay? What we think of as big data, though, often intuitively coincides with this, with the phone,
Fitbits.
which I've put away because I didn't want it to, buzz while I was trying to speak, with Google, with also things that can, medical records is different because there's a certain amount of deliberation about what gets recorded, right? But then again, if you get into wearable devices, you start ballooning into things that. So in part, I think the answer is just that we have it, okay? That our societies have evolved in a way in which some of this stuff is produced by attrition. And in fact, I'm actually a big consumer of podcasts. There are many very interesting podcasts on the new, age of data, okay? If you listen to what they say about the history of Google, literally up to a point, they were just leaving this stuff somewhere with no notion that it had a use, until someone came up with a genius idea of saying, wait for a second, can we mine something out of this? Does it have a...
All this data is being collected in many different ways.
Mm-hmm.
How do we decide, and this may get too super philosophical as well,
Let's try.
There's clear good that can come out of that, but then there's also, I guess, nefarious uses that can, is there a way to control that?
I'm going to say something a bit extreme. You know how people talk about climate change, saying that we may be close to a tipping point?
Sure.
I think this is in the same type of, humongous societal challenges that we have. And we are kind of at a tipping point on this too. Are we equipped to cope with this? It's not entirely clear that we are. That doesn't mean that we cannot become. But, there are many ways many directions from which one could try and tackle this problem, at least partially. Some have to do with regulations, introducing rules, starting with introducing laws that are meaningful from this point of view. Some people talk about transparency as a solution. If there are rules by which you need to put somewhere online all the algorithms that you use to do certain things, that supposedly should allow a certain degree of, should we call it, societal control on what's going on. But then there are lots of issues with that too, because making some algorithms entirely public may have
right.
rather negative, unintended consequences in terms of actors with, imperfect intentions. So one interesting thing, and this actually goes back to competencies that are in the stat department, is that you can think of sort of getting at this from a completely different perspective, which is the one of the algorithms, of the procedures that you design. So instead of saying there is a law that says that X cannot do Y with this data, okay? Or there is a rule that says that every company utilizing certain algorithms needs to make them public, okay? There can be a way of designing the algorithms that allows you to control how intrusive you are, okay? How you can, how deeply you can profile a person, how, what risk of breaking privacy, okay, what privacy concerns. So there may be ways in which you modulate the algorithms to ensure that your profiling doesn't go too deep, and or you are guaranteeing a certain level of privacy, of non-identifiability of subjects and things like that. And this is too a large area of research in statistics on which we have some direct competence here at Penn State. In the stat department here, there's certainly a lot of competence in terms of applications to omics, applications to infectious disease, biomedical applications, climate science, astronomy, and the social sciences. Methodologically, there are lots of people that work on what I was calling reduction approaches, be those feature screens and feature selections or dimension reduction approaches. There are also people working on privacy issues. So, there's actually a lot of competence that we have here at Penn State in the stat department in terms of dealing with this contemporary data that can get big one way, the other, perhaps both, and that has, in so many instances, very important implications for society.
So you just basically mentioned that people in our statistics department are, have their hand in, I think, pretty much every other field of science that we do here in the college.
Actually, this is something that is a very nice characteristic of the stat department. It's very science-oriented. Of course, we do a lot of methods development, and, we think about theory. There is a lot of theory behind the development of statistical methods. But there's been a tradition here, at least for the last 20 years, which has been the time I've been here, for people in the stat department to be really, really engaged in domain sciences. We all have collaborators and important, meaningful scientific applications that we work in. And again, the omics, infectious disease, creating models, climate sciences, astronomy may be some of the examples. Lots of social sciences too. There is something called the Methodology Center that kind of lives at the boundary of biomedical and social. So it's rather interesting to me.
Yeah, and that's actually, isn't that a sort of the history of the development of a lot of statistics as well? I used to study genetics, and
yes,
a lot
for
of the
sure.
early geneticists were also the early statisticians.
Absolutely. And statistics historically is always been very closely linked to scientific questions, okay? Be those of a biotype or from the state, right? The running of the state, the policy making aspects, right? How do you collect data in order to know? So yes, historically, this is a very key feature of statistics. But it is also true that there are many places where statisticians have essentially become more. I don't want to say that we're not mathematicians. I just want to say that you find some communities of statisticians that are more interested in the development of methods or of theories that come behind the methods, and less directly into the science that this can generate or that this is motivated by, because it's circular.
Sure.
Okay? So they're doing their job. Maybe someone else is going to apply their methods. Okay? In this stat department, for some, lucky combination of chance and efforts by the leadership of the department, there's always been people that really have their hands into the domain sciences where techniques are applied. And I like this a lot. I think it's a very, very good feature of the community we have here.
So that was cool.
Yeah, I don't think people realize how integrated statistics is into our everyday lives and into every field of science.
And to think about how statisticians are having to deal with this massive amount of data that's being produced everywhere.
Yeah, and there's so much of it that, like, computers can't handle it sometimes.
Yeah, it's really amazing.
Yeah. So if you want to learn more about Francesca's research or any of the research going on here at the Penn State Eberly College of Science, we'll have links in the show notes below.
Yeah, thanks for joining us on another episode of Hey, I Got a Question About That. If you haven't already, be sure to go back and listen to our previous episodes. Give us a like, a subscribe, and a comment.
Yeah, thanks. But what I want to know is, I messed this up already. I should have just stuck to the script.
Excellent until it.
Thanks. I feel like a sea lion. Someone throw me a sardine.
And today on the pod, she develops methods.
Big data. This is a big podcast, so let's get right into it.
And Francesca studies, no, she doesn't study.
No, she develops.
Yeah. So that was cool.
Yeah, nope.
So that was cool.
Yeah, it's really neat to see. Nope, that's my tagline. It's really neat to see. Eh?
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 Yeah.
No. Oh.
I don't know.
Neither do I.
Yeah, thanks again.
I wonder if they could use satellites to track the hair follicles on top of my head to give the pattern of my baldness.